All right, welcome back. In this video, we're going to practice naming organic compounds. If you thought naming ionic was a pain, you might be right. You probably didn't think that much about covalent. It's pretty easy. Acids, kind of annoying, but all of them are fairly simple with some fairly straightforward rules. Well, that's not going to be that way with organic. It is quite a bit of rules that we have to know to name organic. But don't be discouraged. It is kind of fun in a way. I know that's a twisted, nerdy kind of a thing to say, but there's so many little pieces to the puzzle that most people end up enjoying naming organic compounds. So let me take you through it. First of all, when we name organic compounds, the A1 most important thing to find is the longest chain of carbons. How many carbons in a row are connected? And what we do is assign a prefix based on that number. So you can see here the prefixes for 1 through 10 that we will use. And yes, it does go beyond 10, but we're just going to focus on 1 through 10. It's very similar to the covalent prefixes. 5 through 10 are the exact same prefixes. 5 is penta in both systems, 10 is deca in both systems. The thing that's really unique about organic is how we do 1 through 4. If you remember in covalent, 1 was mono, 2 was di, 3 was tri, 4 was tetra, but not in organic. 1 is meth, 2 is eth, 3 is propyl, or just prop, and 4 is buta. And those are important because they're the most common ones. You use meth and eth so often, so you really have to get used to 1 through 4 here. Let's begin by naming alkanes. Let's back up. Let's remember that alkanes are hydrocarbons that are saturated. They have only single bonds. These are the simplest hydrocarbons. They have the generic formula of CnH2n plus 2. What I would like you to do here, if you don't kind of see that yet, hit pause and draw out 6 carbon atoms in a chain, okay? Or 4, just do whatever. Connect them in a chain, and then I want you to put all the hydrogens around it until you have the carbons completely full according to the octet. And I want you to prove to yourself that that generic formula holds. If we have C6, and you've hit pause now and you've tried it, you should have on there 14 hydrogens, and that will always be the case for saturated alkanes. Okay, so to name it, we're going to get that prefix, and we're going to say ane, the suffix ane, to tell us that it's going to be an alkane. For example, again, if we have C6, it's going to be hex for 6, ane to tell me that it's an alkane, hexane. If it's a cyclic alkane, remember we can have those closed shapes. We'll do the same naming system. We'll just name the number of carbons that are in the closed shape, and we'll put the prefix cyclo in front of it to let us know it's a closed shape. So for example, cyclobutane. As we get into the branches, you're going to have more fun because when we have branches coming off our main chain, we have to tell where they are. We'll use numbers for that. We have to say what they are. So we'll use prefixes like methyl and ethyl and propyl. It's a lot of fun. Let's get to some examples with alkanes. All right, so in the top one up here, I have the long chain, follow my cursor, 1, 2, 3, 4, 5, 6 carbons all in a row. So that's where I'm going to get hex. And then see, they're all all single bonds. Everywhere here, carbon is sp3 hybridized, so that's an alkane, hexane. Very simple. In example 2 here, I have one of those branches I told you about, so follow here. We have to find the longest continuous chain. Let's start on the left. 1, 2, 3, 4, 5. Let's try a different way to make it bigger. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It looks like 5 is the longest I can make. So this is going to be a penta, all single bonds everywhere, pentane. And now, since this is a branch group, let's call this little thing here I'm circling with my cursor, the group is branched off. This is a 2-carbon group. We've learned that 2 is eth. And here's something a little new for you. So here we go. Come follow me. The group itself is a hydrocarbon with 2 carbons. We call that ethyl. So when we have branched groups that are themselves organic, we're just going to take that prefix and put the YL. I don't know if that's a suffix or a root. I think it's a suffix. And that just tells you that it's a fragment. Okay, it's an open spot. So this is going to be an ethyl. And it's on the 3rd carbon in the chain. Count with me. 1, 2, 3. And no matter what direction I count from, it's the 3rd one. So that is a 3-ethyl. 3 telling me where it is. Ethyl tells me what it is. And pentane is my main chain. See, kind of fun. Admit it to yourself. All right, example 3, I have one of those closed shapes I alluded to. So in this one, it's 3 carbons that are closed up. So that is prop. I know you want to say tri, but it's prop in organic. All single bonds everywhere, so it's an ane. So that's a propane. But this is not the propane you cook with. This is a closed shape. And so it's cyclic, and therefore we need to call it cyclopropane. It'll have slightly different physical properties than the propane that you've heard of before. All right, let me say one quick thing about these last 2 that you're probably wondering. In the very top one, this is just a ball and stick diagram. It looks like the Lewis structures you did in pre-AP. It shows all the hydrogens attached. You can't imagine how cumbersome that gets when you're drawing very large molecules, even like 3-ethylpentane in the middle. So typically what organic people do is condense. So this is not quite a condensed formula, but it's getting more condensed. And when you see a carbon like this CH3, that is implied that the H's are all single bonded to the carbon. So that would be like this last piece. See where I'm circling with my cursor? I could write that as CH3. The CH2s just tell me that there's 2 hydrogens attached to that carbon. And that makes your drawing a little easier. And we'll see some other things in our practice in class to help make it easier. Okay, so we're going to talk about alkenes next. We're not going to spend quite as much time because most of the rules are the same. Really now, an alkene, of course, is going to be very different. These are unsaturated. And that means you have to have at least 1 double bond. You can have no triples because that makes it something else. So you have to have at least 1 double bond in there. The naming rules that we just learned are still going to apply, with one caveat. Now the longest chain that you find has to contain that double bond in it. Okay, so you still find the longest chain possible. Once you find it, give it that prefix, meth, eth, propa, buta, whatever. And instead of ane now, we're going to call it an ene because of the double bond. So we can have things like ethene, propene, butene, decene. The only difference is ene. We learned about the isomers, cis and trans, in the previous video. So with these alkenes, we can also give the information about the cis or trans depending on what's happening around that double bond. Are the big branches on the same side of the double bond, or are they on opposite sides? We'll see some practice on that in class. So here are some examples for naming the alkenes. In the top one, we have a pretty straight picture. 1, 2, 3, 4, 5 carbons. So that's going to give us a pentene with a double bond here. The only thing is we have to name where that double bond is. Which carbon does it come off of? Well, we want to give it the lowest number possible. So our choices are off the first carbon or 1, 2, 3, 4. And of course 1 is lower than 4. This is a 1-pentene. Alternatively, you could call it pent-1-ene. That's a little awkward. Most people don't. But some people prefer it that way, and they do that. So be flexible. There's no branches on this one, so that's all we got, 1-pentene. Okay, in the next example, it can be tricky because it looks like the longest chain is 1, 2, 3, 4, 5, 6, 7. It looks like a hepta, but remember it has to contain the double bond. So this is actually a 1, 2, 3, 4, 5, 6. I'll count backwards, 1, 2, 3, 4, 5, 6. Hex is actually the longest chain that we have. So this is going to be a hexene. Now, is this double bond coming off carbon 1 or is it coming off carbon 5? 1. It's coming off, we want it to have the lowest number. So this is going to be a 1 hexene. Now, we have an additional problem with this one in that we have a branch coming off carbon number 2. This again is the 2 carbon branch. It's an eth. So this is ethyl coming off carbon 2. So our full name for this compound is 2-ethyl 1-hexene. Real quickly in the bottom, we have a couple of cycloalkenes. The one on the left is very straightforward. It's a 5-membered ring, so that's going to be a cyclopentene. A number is not important here because when you have just one double bond in a ring, you default to that going to the lowest position. So it is understood to be 1 cyclopentene. And the next one, we have 1-methyl cyclobutene. It's a 4-membered ring, so bute. Here we do say 1 because that methyl doesn't have to be here. That methyl could be over here. And if it was over there, it'd be 2-methyl cyclobutene. So we need that 1 to communicate where exactly that methyl is in reference to the double bond. So those are alkenes. Alkynes are exactly the same naming structure as alkenes, except that the suffix will be YNE. So for the 2 groups, or the 2 carbon groups, we had ethane, for example. If it's a double bond, you have ethene. If it's a triple bond, you have ethyne. Those are the only difference. One quick thing before we do this example, I forgot to mention this for the alkenes, so let's go back to that. Alkanes were CnH2n plus 2. Alkenes have the generic formula H2n. You're asking, where did the plus 2 go? Well, when you have the double bond, you don't have the 3. See this 3 right here on the outside? And this carbon here is limited to what it has. It doesn't have a top and bottom. It only has one or the other. So you're losing 2 hydrogens whenever you have an alkene. And so the alkyne, it's even worse because, see, in this example, there's no hydrogens on the carbon. So you actually have lost 2 more hydrogens. So it's 2n minus 2. All right, in this example, we have in the longest chain that contains the triple bond, 1, 2, 3, 4, 5, 6, 7. I numbered this one for you so you can see it. It's quite a busy molecule. So this is a heptyne. Again, we give it a 2 because I want the triple bond to be on the lowest numbered carbon possible, 2-heptyne. Now, we do have quite a few groups on this one, and in this example, I wanted to show you because I wanted to tell you that when you have more than one branch group, we have to put them in order. But it's not number order. This is what tricks some people. It's actually alphabetical order. We can see here that I have a chlorine coming off carbon 6. That's a chloro group. I have a methyl coming off carbon 4. I have an ethyl coming off carbon 5, and then another methyl coming off. Nope, sorry, that's not a branch. So we just have the 3 branches. So chloro, ethyl, and methyl. And we will put them in that order. Chloro, ethyl, methyl, that's alphabetical. So we see here 6 chloro, 5 ethyl, 4 methyl. That tells us which carbon each is on. It's not in any order. It just happens to be descending order here. It could be 6, 4, 5 if the methyl was on the carbon 5 and ethyl was on 4. That didn't happen here. So our full name is 6 chloro, 5 ethyl, 4 methyl, and then 2-heptyne for the main chain. Isn't that fun? All right, the final class are called aromatics. These are really closely related to the alkenes, and you can make the argument that these are alkenes. Okay, what happens, that double bond in organic chemistry can really do some fun stuff. It can we can form lots of resonance structures when we have these alternating double bonds, and in these aromatics, as you can see in this bottom left picture, see how these double bonds alternate? Well, I could just as easily put that double bond here, which would force that double bond that I have pointed to now into this spot, which would force this one into this spot. And in fact, that's really what happens. in this molecule. Those double bonds are constantly shifting. It's almost like they're spinning like a flywheel. And we call that delocalization. The delocalization of these electrons in the bonds here makes for some very interesting and important properties of the aromatic compounds. So the naming system, we're not going to get too carried away with aromatics, but what I do want you to recognize is that benzene is the simplest aromatic. It is a very, very important molecule in organic chemistry, and I've shown you two pictures here of benzene. I want you to be able to, be flexible and recognize both. On the left, you've seen all the ball and stick. It's C6H6. That's the formula for benzene, and you can see the hydrogen is one hydrogen bonded to each carbon. And on the right-hand side, we've shown the most common way you'll see benzene drawn. A hexagon, that circle in the middle, that represents the delocalized electrons. And in organic chemistry, when we do our practice, you'll see more that every time you have these shapes drawn and there's a vertices with nothing on it, it's understood to be as many hydrogens as possible at that vertices. Okay, and we'll see some more practice on that. But here are some other aromatics that you may come across. If you put two of those benzenes together, we call it naphthalene, as in mothballs. Anthracene, pyrene, benzoapyrene. These seem pretty exotic to you, but believe it or not, they're all around you all the time. If you barbecue something, you're making these PAHs, these polycyclic aromatic hydrocarbons, as the charcoal burns, and they're actually carcinogenic. So there are some people who don't eat barbecue because they're worried about ingesting these compounds. And then at the bottom, some derivatives of benzene that's very important. Toluene is a very important starting material in organic chemistry and organic synthesis. All you do is put a methyl group instead of a hydrogen on one of those spots, and that becomes toluene, synonym methylbenzene. And then the next one is when you put two methyl groups in there. So these are isomers of the same molecule. We call it xylene, and depending on where you put them, we have isomers called metaxylene, paraxylene, and then orthoxylene. And I want you to think real quickly, just looking at those three. We'll ignore the ethylbenzene for now. I think it's pretty obvious how that's different. You can see that metaxylene, the M one, is 60% of all the xylene that forms. Para, the P one, is 14%, and ortho is 9%. Can you tell me why? Think for a moment. Why would ortho be the smallest? Well, I hope you thought about and remembered the steric stuff I mentioned in the last video. Those two methyl groups are pretty close, so they are repelling each other. And so while it can form, there's higher energies involved, and so it tends not to, or it would rather not to, I should say. Well, what about para? If there's steric hindrance, why the heck is para less than meta? And the answer to that, I hope you hit pause and thought about it, is that the meta actually has a mirror image. There's only one way to put one opposite, but what if I put the methyl group over here? That's a mirror image of the one showing now, but they are superimposable because this is a flat molecule, and so there's two different ways I could put that meta to get the exact same molecule. So it's pure probability that you can make a meta. It's just more favorable. Two spots available as opposed to just the one. All right, so that's it for this video on naming basics. There's nothing to do now except practice. But if you have any questions, come by and ask me.